Welcome back to Excel. Today we'll be talking about fitting equations to data, right? How that will help us as engineers and what we can do with that information. All right, let's take a look here. Let's kind of first review what we talked about last time. Last time we talked about analyzing data also. And when we did this, we really talked about looking at single data values, right? X1, X2. We talked about engine cylinder diameters. We talked about test grades, things like that, which are just single data set values, right? And we use statistical information to analyze this data, and we did this using a number of different statistical functions such as average, median, mean, which is the average, mode, min, max, standard deviation. All of those kind of gave a description of what our data set looked like. We also then used histograms, and histograms kind of gave us a distribution, right? It kind of showed us this distribution of how the data kind of curve looked like. And the last thing we did was we looked at a cumulative distribution set, right? Using this same histogram, we were able to create a distribution, cumulative distribution. And what this told us is it told us what the likelihood or probability of let's say a cylinder that was 3.5, if we picked one out, what is the probability that we would get one that size or smaller? We could read up on this, this graph and read over, and we'd see that it'd be 55%. Right? I'm not sure why it's doing that. So 55% means that we will get one that is that size or less. So that's kind of what each of these things showed us. This isn't the only type of data set that we have, which is this single set of data, right? Which is just a value such as the diameter or some dimension on a part. Or our test grades, things like that. Typically we have some relationship between things, and that really is what we call a paired data, right? Paired data has some relationship between X and Y, right? And we're going to look at that type of data. And what these X and Y data sets look like are essentially we have some independent variable, our X, which causes some change, and we have our Y value, which is a variable which is a dependent variable, and it reacts to this change. So an example, something may occur over time. Time is the independent variable, and something changes over time. Or temperature may change, and as the temperature changes, pressure may increase or decrease. That is, then the pressure is the dependent variable on the temperature. Okay, so these are different types of paired data sets. What are other ones that we want to look at, and how we're going to understand these characteristics of an object or behavior of the system? How and why do engineers want to do this, right? Why do we want to really understand this? We try to really understand the characteristics of what's going on. We look at the behavior of the system, right? How it's behaving or acting over time. Also, it allows us to predict future events, right? It allows us to look ahead at something. If we know the dependent variable, we can say what's going to happen in the future and base it off of that. So let's look at some examples of what paired data might be, right? We may have something like I'd mentioned, distance or speed versus distance, right? How far did we go for a certain speed or something, right? We may look at age versus height. A lot of you probably remember when going to the doctor when you were young, they would predict how tall you might be, right? So you had some specific age, you were a certain height, and over time you grew up, right? And they could predict your height, right? Well, I'm at this age here, this old age, where my height is actually starting to decrease. Bad thing for me. I didn't make it to 6 feet, nowhere near it. right? And the last thing we can do is another, not last one, but another example might be force versus deformation. So in springs, springs have a linear property where we have some deformation. We'll call this delta, and this is our force. And as delta increases, so does the force, right? And it's a linear relationship to a point, and then we get into a yield of the material, and then that doesn't stay that way. But most springs always stay and work in a certain range, which is very linear for us. So how do we do curve fitting, right? How do we do it, right? If I give you some information and I give you a graph that looks like this, right? And I give you some data points on here, some different data points, right? And I ask you to put an equation to this line or put a line into this data set, right? Can you do it right now? And I would say everybody can, right? And there's a number of ways of doing it. One is to just kind of take a straight edge, a ruler, and kind of go, okay, right there is probably the best that I can do. It kind of goes through some of the points, not all the points, right? So you can create some line, then from this you can find y equals mx plus b, right? The slope of the line, the intercept, so you have this equation of this line. Everybody could do that. Everybody will get something a little different than each other, but it's probably a good approximation, right? But right now you have that ability to do that. Some people may take it and go, oh, I'll take this point, and there was another point maybe under here, and they may take 2 points on the ends and go something like that and come up with a line. So everyone may come up with a little bit different line, but everyone will come up with some line. So there's methods that are actually mathematical methods that we can use to find these lines or these curves, right? One of them is called using linear interpolation, and the other is linear regression. And we're going to look at both of these. So let's first look at linear interpolation and what it is. And you may already know this right now. Linear interpolation really works with just 2 data points. Let's say we have point x1, y1, x2, y2. So we have this data point here and this data point here. I'm actually going to erase that second one there, and I'm going to make it blue. All right. And we're looking for, in this case, we're looking for the pink one, right? And one way to do this is to use ratios, right? And if you look at this, I can look at x1, y1, and you'll see I have that in my equation here, and it's a ratio, and I have it here also. Those are known values, and then I have x2, y2, and those are here. This allows me then to find my value for x and y. That's this center value here. I can linearly interpolate to find what that value is. And with this equation, we can do a lot of different things. We can have it set up just like this. I can change the order of these things. I can put this one second or first. Same here. I can change the order here, that type of thing. I can even change my x's to be on the top and my y's to be on the top. But I must keep this same relationship. If I use y's on the top, I need to do it through the whole thing. If I do x's, I need to put x's on the top for the whole thing. And I need to keep kind of the same relationship. But it doesn't matter which one goes first or last. The other way of doing this, and a lot of you already probably know this, is you can use find the equation of the line, right? Y equals mx plus b, right? And m is our slope, right? M is our slope, and slope is equal to rise over run, and our rise over run. So if we look at this, our rise is in the y direction, so our rise is y2 minus y1 divided by our run, which is going out in this x direction, x2 2 minus x1. That's that distance. That is our slope, right? I can put that into this equation. And then how do I solve for b? How do I solve for this y-intercept b? I now know my slope m. All I have to do is put in one of these points. So I could put in either y1 or y1 and x1 or y2, x2, and I can solve for b. Once I know b, then I have my whole equation, y equals mx plus b. Now if I want to determine what my value is, I need to know one of these, right? If I know x and I want to find y, I would put in my x value and I can solve for y. Same with this relationship here. I can put in a value for x and solve for y. Okay, so it's a little bit of math that we need to use, a little bit of algebra to kind of solve this, but it can be done. It's not too difficult. Can Excel help us with this? Why, sure it can. There's a formula or a function called forecast, and for linear interpolation, we can use this forecast function. It calculates or predicts a future value along a linear trend by using existing values. Linear trend, so it's assuming it is linear and not curvature. So it's some linear trend, not a curved trend, right? Those give us different results. Okay, and we can use this function. I'm going to erase this so we can kind of see this a little better here. And it's called forecast, and what we do is we have some value of known x. We will plug that in. We know a range of y's, and what we like to do is use the values just right around that x. So if I do this line here and I know my point, I know this point there, and I know this point there, and I'm trying to find this one. This is my known x, and I don't know y, right? I want to take my closest points that I know. I don't want to use all of the data. I just want to use the data around each of these ends. Okay? So the x values are known independent variable. That's this x here, the red x actually, that you use to estimate. And then the range is the highlight of the cell of the address containing the ranges for the x and y's. Okay? Let's take a look at how we use that real quickly. Okay, here we are in our Excel file. What I have here is some value of x and y, and I want to see what the value is between them at x equal 2.03. And I can use that relationship. This is that relationship of the ratio, right, that you can do, and you could create that formula and solve for it, right? I'm not going to do that right now. That's a lot more complicated. We're going to use the Excel function forecast. We'll find that that is much easier. Forecast, and it says, what is our known x? This is our known x value. It's asking for known y's. It is, we only have these two. Those are the ones we want, and our known x's. That's those two. Close parentheses. And you see we get the exact same answer. Okay? Let's look at this problem here. This is some temperature, and it changes for heat capacity. And we want to know what is 80 degrees, what is the heat capacity? Well, 80 degrees isn't on my data set here, so how do I solve that, right? I can use forecast. I know it's got to be between these two. And I will show you that if we use equals forecast, our known x is the value itself that we know, and we're looking for a y. And so what is our known y's? We're going to pick just those two because it's between 80 degrees is between 0 and 100, comma, and our known x's. These are our x values. And if I hit enter, close parenthesis, hit enter, I get 0.11454, which makes sense. It's in between here and a little closer to the 1168 value. If I did this way, and I will guarantee a lot of you will do this, and this is incorrect. If I take this 80 degrees and I do all the values of y and all the values of x, you will see I get a different answer, right? And it's going to be a wrong answer. And the reason being is if I look at this, I'm going to actually look at the graph of that. What does this thing look like? Using a scatter plot, you can see that, add in a line. Oh. And I will move this line here to the end here. And this one to the end here. And you can see that the one, if I use all the data, that I'm actually off by a little bit. So if I could zoom into just this area here, which I could do, you will see that that is off. Let's kind of take a look, see if we can find that. I want to, oops, sorry. I want to my x-axis. I want to change that. Oh, I'm sorry, I should click this. All right, format x-axis. And I only want to go to, let's say, 50 to 100. And then I want to look at my y's. And I only want to go from 0.1 to 0.12. Okay, so you'll see that there's some difference at 80. There's some difference between these two. So that's that error that we're seeing in here. That was a long way to get there, but there's this error that shows up between these two. Okay, so we want to not do that. We only want to take the data points right around it, right? So we just want to go between these two. And this actually is really not there. It's off this way somewhere. It's not coming out quite right. But there'll be some error in there if I could have zoomed in better. I'm sorry about that. So we don't want to use all of the data. We only want to use the points around it. That's what that whole thing was about. Sorry for the long-winded talk about that. Let's look at the next one, forecast 335. We see that it's between 300 and 400. So here's my value of my x. I'm between these two. And then this is my x's. And we come up with a value of 0.14356. Next one, forecast. X's, we're at 410. So that's that one, and it's between 4 and 500. And there's our result, equals forecast. And again, this file is on the class website also, class web page. 675, here and here, and here and here. Those are pretty easy. Now the question is, 705, that's not between anything. How do I deal with this? We still can use forecast. It's going to extrapolate, meaning going beyond. Interpolate is to go in between 2 points. Extrapolate is to go beyond them. So we're going to extrapolate this data. So I'm going to go from 705, and I'm going to take the last two data set in this case. All right, and do that. That should be all right. Oh, I didn't put a comma in there. That was my problem. Let's fix this. Sorry about that. I didn't pick this one first. All right, and there, and there. Oh, and too many parentheses. But there we go. So we see it's greater than, it's out in that point. So that's how we can extrapolate. What if about the other way? Look, I'm given a y value. Now I want to know the x value. How do we do that? Our forecast always says to use, look, forecast. It says, oh, we want the x values. But if we think about it, we can reverse this, right? Let's just think about it being reversed. So we have, I'm going to make this bigger so I can see this out this way. I'm looking for this 165. Well, I know it's between here and here, 500 and 600. So I'm going to pick this as my x value, comma, and it's between here and here, so I'm going to pick this as my known y's, which are really my x's. I'm just switching the order that they occur. And if I do this right, I get 523, which makes sense. It's in between 5 and 600. Okay? You may want to reduce the number of decimal places. All right. Here we can do this again. This was just another linear interpolation example for just these. Some x value given this, given that. Okay. So that is our using the forecast function. Next, we want to look at how do we use linear regression or least squares. Let's take a look at that. Okay, so now we're going to look at linear regression, or something called least squares, method of least squares. And this has a very complicated formula to it. This is the example where I said, okay, what if we take some values, and it's all these circles, right, and I put them on a graph, and I give you a ruler, you can find some line here, right, that kind of fits it, right? It's kind of in between. The mathematical way of doing this is it's looking for that specific line, which you see this air in y, these little lines going up and down, where that is the least distance or the smallest amount of air for each data point. It goes through a regression method where it goes through multiple steps to be able to find that specific line for each of all of those points. Okay, and it's a rather complicated formula. We aren't going to even look at it. We aren't even going to touch it because Excel does it for us, right? It also finds us something called a correlation coefficient, which tells us how exact it is to the data that's been given to us. So again, we can do this by using something called trend line. And if we generate a graph, first just generate a graph itself of data, we can find an equation that best fits it. We can use something called as correlation coefficient, or R squared value. And if that R squared value is 1, it is perfect. It means that that line fits through every single point. If it's not 1, it might be 0.9, which means it's like 90% close, or 0.2, which is really horrible. It's like 20% or something. So the closer that value is to 1, the better off we are. So it's between 0 and 1 is our value. And we can choose different types of trend lines that will give us the best correlation. Typically, we will concentrate, though, on straight lines. The steps for doing this is to first create a table of data. Independent values on the left column, so that's our x values, are dependent on the right column, so the column right next to it. That's our y values. We create our xy scatter plot, our xy chart. with coordinates and do not connect the points, so we don't want them connected in this case. And then we're going to click on one of the data points, and then we're going to go to chart layout or right click and select the trend line, and then we can add a trend line and choose the type and everything. It's very simple to do. Let's take a quick look at this. Okay, so here we have some data, distance and force. This is for a spring, it looks like. Let's take a look. We can highlight this data. I'm going to zoom in a little bit more, right? And highlight that data, and we will go to insert, and we want to go to scatter, right? We're going to put one in without any line, right? So here's our scatter plot, right? We can do and this is force versus distance. And this is force in newtons. Okay. So there's our graph, right? But we want to be able to add in our trend line. We want to find one that fits it. So I'm going to click one of the data points. I'm going to right click, and if we go down here, second from the bottom, it says add trend line. I'm going to click on that, and you'll see that we have a list of different ones. We're going to look at the linear one first with this data set, right? So here's linear, and I'm going to display the equation and what we call the R squared value that tells us how well it correlates. And then I'm going to just kind of close this out. So here is our equation of the line. So now I can say for any distance x, I should know what my force is in newtons. And this has an R squared value of 0.957, which is very good, right? Almost 0.96, 96% or so. So that's very good. So I can, for any value of x, I can give you the force and the y, right? The force in newtons. Or let's say I'm applying a force, how much is it going to compress that spring? I can go the other way, right? I can put in a y value and solve for x. So most relationships are linear, but not all, right? So let's take a look. I could also, let's format our trend line. Let's suppose we could click exponential, right? And we see we can throw in an exponential. It changes the equation. You see our correlation actually isn't very good with that, right? Logarithmic we're not even going to deal with, but we might do some powered one. 0.98, that's pretty good. But we know springs typically are very linear, but this would be a very good equation. Also, the other one that we might look at is polynomial, right? And you see I got 0.97, and this is only for a second order, so it's x squared value, right? I could increase this more and more. There's a fourth order polynomial. You see already at fourth order, I'm already at an r squared equals 1. It goes through everything. Well, I know there's a fifth square. There isn't even a fifth squared. 6, it goes up high, but 4. I know that there is no spring that acts that way, right? So this is kind of crazy when you get these orders up very high. Other than second order, when you're down to second order, that may be realistic. Third order, it could be okay. More than that, it kind of gets a little funky, and we don't really deal with that. But usually second or third is okay. Otherwise, we stick with our first order, which is linear, and that's what we will do with this. Really, that's it, I believe, for doing trend line equations. We can look at one more example real quickly, and then we'll call our quits. We'll look at this example here. We have one with weight versus car mileage, right? And we can highlight this, create our graph again real quickly. We're going to create a scatter chart. Boom. I don't like this. This arrangement of the data is not good. Let's format our axis, right? I want this to be about 2,000. And let's look at the y. Let's put that up to 15 for our minimum. There, that looks a little better. Now we're kind of filling in the chart better. I'm not going to add this in. I didn't put my name and date on the other one. I'm not going to do that all right now. We're just looking at trend line right now. But for your homework, you should fill out the graph properly by putting in the, the title as weight versus mileage, right? And you should put in your X and Y axes. You should, if it needs a legend, you should do that also. Let's click on the one data point. Let's add a trend line. And if we see we have our equations here and here, our R squared. You see our R squared values rather poor at 0.64 for a linear relationship. So maybe this one doesn't have a linear relationship between weight and mileage. Maybe there is some exponential. It's a little better. 6.8 before it's 6.4. How about powered? 7.1. That's not bad. Here's a 7. We're a second order. 7.3. And that kind of looks a little weird. I may end up going with a powered one. Might be what actually is going on in this data. So there's a number of things, because this is only weight versus mileage, let's say, of a vehicle. There's also other things that come into play that may make some of these data points off, right? If we think about it, there's wind resistance, right? Some vehicles are more aerodynamic than others, so there's more things that come into play than just the weight itself. So, but we can kind of see these different relationships between these different curves and how they fit with our data set. Okay? So hopefully this helps explain this for you. If you have questions, always ask me at any time if you need help with any of this. Thanks, and have a great day.